Hello everyone. For the beginning, I'd like to thank my co-authors Haipeng and Bo. We begin by a simple determined environment. The rat will choose one of the 6 points in the edge to evade the dog, and the dog needs to predict where the rat goes. If the predicted position is the same as the position of the rat is caught, like in this figure. Then human will usually think the action of the dog is good. However, what if the rat follows a distribution like this, where the optimal action is 3 rather than 2? Is the action still good? Are the non-optimal actions 1 and 2 the same? With these questions, I first briefly introduce the problem statement. In our setting, an agent chooses actions given states. Then human will give feedback to the agent, and the agent needs to infer the best action according to human feedback. In this process, human may not provide feedback when they feel confused or they use different strategies. Lofting et al. Mentioned that if people have experiments of training dogs, they are prone to not punish the agent when non-optimal actions are chosen. The second challenge is that trainers may not know exactly the optimal action, mainly because suboptimal actions sometimes can obtain huge reward. Then human will provide positive feedback to suboptimal action and negative feedback to the optimal action. The third challenge is that non-optimal actions may have different levels of optimality because rewards of different actions are different. Then how to learn behavior efficiently with uncertain human feedback. Most of existing works doesn't consider the situation that human doesn't give feedback. However, Lofting et al. Consider no feedback, but they assume that positive feedback can only be given at the optimal action, and non-optimal actions are with the same level of optimality. These assumptions may not work well in environments with uncertainty. Our contributions are threefold. We propose a human feedback model considering uncertainty and a novel algorithm learning the optimal actions and update human feedback model simultaneously. We also conduct external experiments, including human participants. We model the uncertainty by a human feedback model. The model includes 3 functions that correspond to 3 types of feedback. Since the sum of these 3 functions given an action is 1, the last function is actually 1 minus the sum of the probability that human gave the other 2 kinds of feedback. We assume that at the optimal action, the probability of positive feedback is the largest and the negative feedback is the smallest. There are 3 parameters. Lambda is the optimal policy. Mu and sigma control mean and variance. Formally, we can write the function as product of 2 parts. The echelon in the second equation is a tiny positive constant to prevent that p minus equals to 0. For example, p can be Gaussian function and a logistic function. Then to learn these 3 parameters, one popular way is using MLE with EM algorithms. However, if we treat mu and sigma as latent variables in the EM algorithm, the integral of EM is hard to calculate because there is no bound of sigma, and the triple integral is also hard to calculate. Our solution is to use an alternating optimization method that combines EM and GD. Mu is treated as a latent variable in EM and is eliminated in GD. Firstly, we update lambda with sigma fixed. Since mu is bounded, we can treat it as a latent variable in EM and calculate the integral by numerical method. Secondly, we update sigma with lambda fixed. Since the E hat is actually the ratio between the probability at action A and the maximal probability of receiving positive or negative feedback, we can eliminate mu by division, and the loss function is the MSE of two ratios. In the experiment part, we first do the rat catching experiment. At the beginning of each round, the dog is at the center and the rat is at one of the 4 edges. Then the rat will move to one of the 6 points following a fixed distribution. The dog needs to predict a point to go before the moving of the rat. We use the number of steps to finish training, the number of rats caught per step, and the gap between third and the optimal pulses as metrics. We can see that our algorithm performs the best. The second experiment is learning users' preference of lighting. States are reading, watching videos, and talking with others. Actions are different light levels. The results are shown in the table and figures. We add a query method which is asking participants to select their preferred light levels. This method is to show that the human sense is inaccurate. We also conduct simulated experiments to show the performance of GD method when the sigma equals to 1. Our algorithm can learn the value of sigma with enough steps. The only exception is that the situation that the number of actions is 3 and the number of states is 2, which is very simple. Our algorithm converges to the optimal policy repeatedly and then the experiment ends. Thus, we do not have enough data to obtain the true value of sigma. In the robustness experiment, we generate users randomly and compare with the algorithms with fixed sigma. The results show that our algorithm performs the best. In conclusion, we propose a new model of human feedback and algorithms that combines EM with GD, which can learn the optimal policy and update the feedback model simultaneously. Our experimental results demonstrate that our algorithm outperforms baselines under multiple metrics. That's all. Thank you.